Hi everyone, and welcome to Lecture 8, Molecular Geometry, VSEPR, and Polarity. We're going to start this lecture by recapping some really important topics that we've already covered. These topics are so important that they're preliminary to understanding VSEPR. I'm not going to go into great depth because we have already covered them, but if you're finding that you don't understand or you have gaps in your knowledge, then go back to the lectures that cover these topics and definitely work through all of the examples in those lectures until you know this information solid. The first topic we're going to recap is ionic bonding. And with ionic bonding, we're always looking at transfer of electrons. This requires the presence of two elements, a metal, which is going to donate an electron so that the metal can gain the electron configuration of the Nobel gas that's closest to it, and a nonmetal that will accept an electron so that that species can get the electron configuration of the Nobel gas that is closest to it. And the ratio of positive and negative ions combine to that which achieves charge neutrality. So an example of that, if we had sodium is going to give up one electron so that it can get the Nobel gas configuration of neon. That's going to give sodium a +1 oxidation state. For a nonmetal, we could look at chlorine. Chlorine is going to give up one electron so that it can get the oxidation state of the Nobel gas closest to it, which is argon. And that is going to give chlorine an oxidation state of -1. +1 - 1 cancels out, and so we end up writing the ionic compound, sodium chloride, NaCl, in a 1 sodium to 1 chlorine ratio, and that gives us charge neutrality. In other words, we would never write this compound, sodium chloride, like this in a 2-to-2 ratio because that is not the lowest whole number ratio that gives charge neutrality. The exception is polyatomic ions, where we don't have charge neutrality. That is the smallest whole number repeating ratio of ions that are present, and their oxidation states sum to the charge that's on the polyatomic ion. If we had another example for an ionic compound of potassium and sulfur, potassium, of course, will give up one electron so that it can get the Nobel configuration of argon. And sulfur wants to gain 2 electrons to get the electron configuration of argon. Therefore, we'll need 2 potassiums to 1 sulfur for this compound to get charge neutrality, and that is potassium sulfide. Recapping covalent bonds, we're talking about shared electrons now. And so with shared electrons, we can have an example of H2, where each hydrogen that's involved in this bonding interaction is going to donate 1 electron to this bond. And then they're sharing. So each hydrogen actually has a duet, which gives it the electron configuration of the Nobel gas closest to it, or helium. These covalent bonds can form between 2 identical, as we just showed, H2, or similar elements. For example, O2 or NO2. Those are nonmetals, and so they are similar elements, O2 being identical and NO2 being 2 elements that are both nonmetals and therefore are similar. We refer to these compounds not only as covalent compounds, but as molecular compounds, and so they form molecules opposed to ions. They contain both bonding and non-bonding electrons. And if we look at ammonia, for example, and draw the Lewis structure of ammonia fairly quickly here, you can see that we have bonding electrons between the nitrogens and the hydrogens. And then we have non-bonding electrons in the lone pair that gives the nitrogen a perfect octet. Coordinate covalent bonds also share the electrons between the two atoms, but both electrons come from one of the two atoms that's involved in the bonding interaction. This allows an atom with multiple vacancies in its valence shell to share a pair of non-bonding electrons that's donated by another atom, and explains a deviation from normal bonding patterns that we see. For example, oxygen has two vacancies in its valence shell, and if we wrote the Lewis structure for oxygen, we would be able to see that because oxygen has a valence of 6. And so there's a vacancy that I'm showing on the left and the right side of that oxygen. If we consider something like chlorous acid, is this one, and we quickly write the Lewis structure. And I've already drawn the structure. I just need to distribute electrons around this structure to give every species in this structure a perfect octet. And now the next thing I'm going to do is have a look at where the electrons actually come from in this bonding interaction. And so I know that one of the electrons in this HO bond came from the hydrogen. And I know that oxygen has a valence of 6. So I'm showing with two lone pairs 4 of those 6. There's another electron here in the bond that's shared with the hydrogen. And there's another electron here in the bond that is shared with the chlorine. The oxygen at the other end also has a valence of 6. So I can knock out where those electrons are coming from right now, and I have 3 lone pairs. That is 6 electrons. And that oxygen does not have another electron to donate to that bond with the chlorine. If we look at chlorine, we know that chlorine has a valence of 7. So if we account for chlorine's electrons, here's 1 in the bond that it's sharing with that oxygen. Here is the lone pair and the second lone pair. So that gives us a total of 2, 4, 5 electrons. Here is number 6, and here is number 7. That is chlorine's valence, 7 electrons. And so you can see how this bond right here is coordinate covalent. In other words, both of those electrons were dedicated to that bond by one of the 2 atoms involved in the bonding interaction, and that is chlorine, donated both of those electrons to that bond. I want to recap electron orbitals a little bit, electron configurations and electron orbitals. Electron orbitals are found within a subshell where electrons can be predictably found about 90% of the time, as we've discussed in the past. Each orbital contains a maximum number of 2 electrons. So in the S subshell, we have 1 orbital. That means we're going to have a maximum of 2 electrons. In the P subshell, we have 3 orbitals. That means we're going to have a maximum of 3 orbitals times 2 maximal electrons per orbital gives us 6 electrons maximum in the P subshell. D contains 5 orbitals. And so that is 5 orbitals times 2 electrons maximal in each one of those orbitals gives us a total of 10 electrons in D. F subshell contains 7 orbitals, so that is 7 orbitals, and again, a maximum of 2 electrons in each of those orbitals, which gives us a total maximum of 14 electrons in F orbitals. In terms of the shape, the S is spherical. The P has two lobes like a dumbbell. The D has four lobes that reach into four corners of a square. And the F has 8 lobes that reach into each corner, such as a cube. Orbitals in the same subshell have the same shape, and they differ in orientation about the nucleus along the x, y, and z axes. So for example, a p orbital, there are 3 two-lobed shapes in the p subshell. P orbital has 2 lobes. One will be on the x-axis, one on the y-axis, and one on the z-axis. And each of those 3 can hold a maximum of 2 electrons for a total of 6 electrons in P. We could have a similar discussion and have had similar discussions in the past about d orbitals and f orbitals. Lewis structures is very dominant in determining three-dimensional structure and looking at VSEPR models. You need to be able to draw Lewis structures very quickly because that is a first step. That is step 1 in being able to make determinations about three-dimensional structure in small molecules. Lewis structures we've looked at, you can draw Lewis structures for ionic compounds and covalent compounds. Lewis demonstrates how valence electrons are involved in bonding. The bonds are represented with 2 electrons each, and we have single, double, and triple bonds. And lone pair electrons that are positioned as shown in the most energetically favorable places surrounding an atom or a compound structure. So VSEPR is a model that we use to predict three-dimensional geometry of small molecules that only contain a few atoms. VSEPR uses Lewis structure as the ground formation of this three-dimensional model. And then we look at the valence shell electrons and adapt that three-dimensional structure to minimize the repulsive forces of the electrons. To recap a little bit on quantum mechanics, these red arrows are showing you repulsion. These little blue spheres represent electrons, and so you can see that we have electrons in different energy levels that are increasing distances from the nucleus. There are repulsive forces between the electrons that are in the same energy level, and there are repulsive forces between electrons that are in different energy levels. Notice the blue arrows that are showing us attractive forces to the nucleus. Now, of course, we would not only have the blue arrows showing us attractive forces to the nucleus from the outermost electrons, but also from these electrons that are closer to the nucleus. They're still also going to have attractive forces because the electrons are negatively charged, and the nucleus, of course, is positively charged. The outer electrons are called the valence electrons, and the inner electrons are called the core electrons. Notice that the outer electrons, the valence electrons, are shielded from the positively charged nucleus by the core electrons. This means that those outer valence electrons are going to have more energy and be more reactive and more excited because they don't have that positive charge attraction as strongly as the core electrons do. In looking at electron repulsion and examining ammonia, let's just look at the Lewis structure of ammonia. So there's the Lewis structure of ammonia. We can see that there are 2 electrons in each bond. And what's interesting about those 2 electrons that are in each bond here is that they're being held or tethered, if you will, between 2 positively charged nuclei, between the hydrogen nucleus and the nitrogen nucleus. So those positively charged nuclei that are flanking either side of those electrons are holding them in place much more stable. And so we see the electron cloud, this white electron cloud that I'm going to outline a little bit here. We can see this electron cloud associated with the electron density in these bonds. And you can see a bond here and a bond here. The third bond, which is back here, we can't really see because it's hiding behind the nitrogen, but there's a nitrogen-hydrogen bond in the back as well. We can see it in the Lewis structure. Here's one bond, here's a second bond, here's a third bond. So those 3 bonds containing 2 electrons each are going to repel one another very strongly, and they're going to move apart as far as they possibly can. And when they move apart as far as they possibly can, there's going to be some angle or degree that's associated with that movement. If we continue to evaluate the Lewis structure of ammonia, and again, I'm going to quickly draw the Lewis structure here. Now we're looking at this lone pair on the top, and I'm going to outline the lone pair's electron would be if you compare the lone pair's electron cloud to the electron cloud that's associated, this white electron cloud down here that's associated with those that are being held by 2 nuclei. This lone pair is only being held in place by 1 nucleus, and that is the nitrogen nucleus. So there isn't as much positive charge stabilizing these negatively charged electrons. And therefore, their electronic field and their associated energy with that electronic field is huge compared to the 6 electrons that are involved in the bonding interactions. This is going to have some real strong repulsive forces. And those really strong repulsive forces, what they do is they press down on these bonds that are in the structure, and they compress those hydrogens closer together because, again, that electronic energy is pushing against them. So if we looked at the Lewis structure and drew the same thing, we would see this big electron cloud up here pushing down on these bonds right here and compressing these 3 hydrogens closer together than they otherwise would be without that electron pair there. The distance maximization for these electron arrangements, we view that around the central atom. So we're looking at the central atom and we're saying, what are the electron arrangements surrounding that central atom? So number 1 step is draw the Lewis structure. Number 2 is look for these electron arrangements around the central atom, and I'm going to give you some examples about how you do that. First, though, I want to tell you we're only going to cover 4 different electron groups that are surrounding that central atom. So if we have 2 electron groups surrounding that central atom, the bond angle is 180 degrees, and this is associated with a linear geometry. If we have 3 electron groups surrounding that central atom, the bond angle is 120 degrees, and that is associated with a geometry, a 3-dimensional geometry that is called trigonal planar. If we have 4 electron groups surrounding the central atom, that is associated with 109-degree bond angles, and the geometry is called tetrahedral. You have to commit this to memory. So again, 2 electron groups, 180 degrees linear. 3 electron groups, 120 degrees trigonal planar. 4 electron groups, 109-degree bond angles, tetrahedral. So here are the basic electron arrangements, and you notice that I have electron underlined here. So we're looking at electron arrangement geometry first. Then we will look at molecular arrangement geometry. Again, this table is showing us what we looked at on the previous slide. 2 electron domains. This is electron domain 1, this single bond. This other single bond is electron domain 2. 180 degrees linear. 3 electron domains. This is electron domain 1, 2, and 3. That is 120-degree bond angles and trigonal planar electron geometry. 4 electron domains. This is electron domain 1. This bond is electron domain 2. There is a single bond here that is electron domain 3, and another single bond over here that is electron domain 4. 109.5, but I'm just going to ask you to memorize 109 is fine. And this is a tetrahedral geometry. What is the difference between an electron pair and an electron group, which is also called an electron domain? Now, unfortunately, in Tyler DeWitt's video, he calls an electron group or an electron domain, or a VSEPR group, it could be called, which is the proper chemical scientific term. He calls it a thing. It's not a thing. These are electrons. They're electrons that are in a region surrounding the central atom, and they're called electron groups, electron domains, or VSEPR groups, or VSEPR domains. So what is the difference between an electron pair and a VSEPR electron group? How do we distinguish between these two? Because so far it looks like we've been looking at single bonds. There are 2 electrons there. That sounds like an electron pair. Well, it is an electron pair. Pairs of electrons exist in bonds. Pairs of electrons exist in a single bond. So there are 2 electrons or 1 pair in H2. In a double bond, we have 2 pairs of electrons, or a total of 4 electrons. And in a triple bond, like we have an N2 here, there are 2, 4, 6 electrons, 3 pairs of electrons in that triple bond. We can also have pairs like that on ammonia over here that are not involved in bonding interactions. So how do we distinguish that from an electron group? With an electron group, again, we're looking for the groups that surround the central atom. And the VSEPR electron groups include all of the following. 1 electron all by itself, which sometimes you haven't seen it yet, but you may before this course is over. It's called a radical, where you see 1 single electron all by itself. That's 1 electron group, 1 electron domain, or 1 VSEPR group. You could see 2 electrons. That would include a single bond or a lone pair. The single bond is equal to 1 electron group. A lone pair is equal to 1 electron group. 4 electrons. A double covalent bond, for example, also equal to 1 electron group, or 1 VSEPR group. 6 electrons, or a triple bond, for example, also equal to 1 electron group. So we're looking for a region where there's a cluster of electrons together, and we're calling that an electron group because it has negative charge radiating from it. So let's distinguish between these structures that we have below and determine how many VSEPR electron groups there are associated with the central atom, and then relate that number of groups to the bond angle. Again, this needs to be committed to memory because the number of electron groups is associated with a specific bond angle. So let's start with HCN, hydrogen cyanide. So if we start with HCN, we're going to look at the carbon because that's the central atom. How many groups of electrons, how many VSEPR groups do we have? Here's one, and here's two, because remember, a triple bond is one electron group. So we have a total of 2 electron groups here. Two electron groups is 180 degrees. Again, how do I know that? Because I commit it to memory. So this electron structure is going to be linear. 180 degrees is linear. Again, I commit that to memory. Let's look at this carbon down here on CO2 because that's the central atom. We have one electron group here, a second electron group here. So again, we have 2 electron groups. That's 180 degrees. So when we look at this interaction, and we can do it with the other one as well. This bond angle right here is 180 degrees. Up top, this bond angle right here is 180 degrees. That is linear. Let's look at SO2. How many VSEPR electron groups surrounding the sulfur, which is the central atom, because it is flanked by 2 oxygens? 1, 2, the lone pair counts as a group, and 3. Double bond counts as 1 electron group, single bond counts as 1 electron group, lone pair counts as 1 electron group. So that is 3 electron groups. That is 120 degree bond angle, and that is trigonal planar geometry. The bond angle here is 120 degrees. If we look at this structure over to the far side, this is called formaldehyde. Carbon is the central atom here, flanked by 2 hydrogens and an oxygen. We have 1, 2, 3 electron groups. Each single bond counts as an electron group. The double bond counts as an electron group. So 3 electron groups. That is 120 degrees bond angle. That is, again, trigonal planar. This bond angle right here is 120 degrees. So is this one. This is just a solution for the previous slide. You'll notice that this slide doesn't have the electron geometry, but I do want you to know the electron geometry because it has been opened up in discussion on a previous slide. So let's have a look at these 3 structures. Again, VSEPR electron groups, electron geometry, and bond angles is what we're looking for here. How many VSEPR electron groups do we have? Here's 1, 2, 3, and 4. And it doesn't matter how I number these. I could have gone counterclockwise. I could have started in a different place. It doesn't matter. We're just counting all the electron dense regions that are surrounding that central atom. So we have 4 electron groups. 4 electron groups is 109-degree bond angle. The electron geometry is tetrahedral. Again, electron geometry is tetrahedral. We have to be careful because we're looking at electron geometry and then we're going to look at molecular geometry. If we look at the next one, 1, 2, 3, 4. Each single bond counts as an electron group. Again, we have 4 electron groups. So what's the bond angle? Approximately 109. The electron geometry is tetrahedral. Look at the last one over here. We have 1, 2, 3, 4. Each lone pair counts as an electron group, and each single bond counts as an electron group. 4 electron groups. What are the bond angles? 109 degrees. And the electron geometry, tetrahedral. So you see the electron geometry is tetrahedral if we have 4 electron groups, and it doesn't matter for the electron geometry if those 4 electron groups are bonding or non-bonding. The other thing I want to point out to you with this slide is sometimes students get a little confused with these wedges. So this is a wedge and these dotted lines. And so this is what I mean by a dotted line. The wedge just means that that particular hydrogen is coming forward towards us out of the plane of the PowerPoint slide. The dotted line means that that particular hydrogen is going back away from us out of the plane of the PowerPoint slide. The straight line bond that you see here, that is indicating that that particular hydrogen and its bond, so the nitrogen and the hydrogen and that bond are both in the plane of the PowerPoint slide. Here is the solution for the previous slide. Again, doesn't have the electron geometry, but I would expect you should know that since we've covered it already on a previous slide. So let's talk about the structural rules for 2, 3, and 4 VSEPR electron groups, and we're not going to go beyond 2, 3, and 4 VSEPR electron groups in Chem 100. That will come later in majors chemistry. So step 1, literally, is draw the Lewis structure. That's what you have to do first. You cannot make a determination about the bonding and non-bonding electron groups unless you draw the Lewis structure. Then you identify the atom that you want the geometry for, and that's typically the central atom. I will show you some examples of cases where we have more than one central atom at the end of this VSEPR lecture. You determine the number of VSEPR electron groups that are present about the central atom, and literally that's step 2. So you draw the Lewis structure, then step 2, you count how many VSEPR groups you have, and you distinguish between bonding and non-bonding if you're after molecular structure. If you're after electron structure, it doesn't matter. You don't have to distinguish between bonding and non-bonding. But if you're looking for molecular structure, which is what we're going to do next, you need to determine how many bonding electron domains do I have and how many non-bonding VSEPR electron domains do I have. You're looking at lone pairs, single, double, and triple bonds, each considered to be one electron group, because each represents one region about the central atom. And then we predict the bond angle and the geometry because we memorized. For small molecules, we memorize the bond angle and the geometry that is associated with a specified number of bonding and non-bonding electron domains surrounding a central atom. And we know that the electron groups are going to orient so that the repulsive forces are minimized. So they're going to push as far apart as they can to minimize the repulsive forces. They can't leave the structure They're stuck on the structure, so they can only push a certain distance and then stop. Why do they push apart that distance? Because those domains have electronic charge that is repulsive. It's a force. It's a repulsive energy between the electrons. And if you have bonding domains, and I showed you this before with ammonia, I showed you that the nitrogens and the hydrogens are sharing 2 electrons, and those 2 electrons are tethered between these 2 nuclei. And so if we have 2 electrons in here that I'm sort of drawing green dots, they are tethered between 2 nuclei, a nucleus here and another nucleus here. Remember, those nuclei have positive charges, while those electrons that are in the center, maybe I should have drawn them in a different color, so I'll do it right now. They have negative charge associated with them. Negative and positive charges attract. And so you have an attraction force here that is stabilizing those electrons. On the bottom of this screen, you can see that we have only 1 nucleus and we still have a lone pair here. So we still have 2 electrons here. Both of those electrons in that lone pair have negative charge, but there's only 1 positively charged nucleus to stabilize both of those electrons. And so we have a much greater electron density associated with our electron cloud because we have a whole lot more energy now because we don't have as much attractive force to stabilize. That means that a lone pair is going to have a lot of energy that's going to push on other electrons that are anywhere in its vicinity. If those other electrons are bonded electrons, it's going to push not only those bonded electrons, but the atom that is bonded to them away from the lone pair. And this is going to contract a lot of atoms a little bit closer together, and you'll get slightly different bonds. Now, in Tyler DeWitt's video, he's asking you to memorize all of these different bond angles. I'm not going to ask you to memorize all of these different bond angles. You'll see as we go through examples that I'm going to want you to be able to explain what's going on, but not memorize all the different bond angles. I want you to just say, we have 4 electron groups, therefore the bond angle is approximately 109. It would be slightly compressed because there's a lone pair at the top pushing, repulsing the electrons that are in the bonds, and therefore compressing the atoms together a little bit. So now we're going to look at molecular geometry before we looked at electron geometry. Notice that if we have 2 bonding domains, no non-bonding domains, 2 bonding domains, we have 180 degrees in our molecular geometry, and the structure is linear. This is no different when we have 2 bonding domains. This is no different than we had with electron geometry. Exactly the same situation here. We have 1, 2 electron domains, and notice we have 1, 2 atoms that are associated with this molecule. Those 2 atoms are 180 degrees from one another, and those 2 electron domains are 180 degrees from one another. And so that makes the electron 3-dimensional structure and the molecular 3-dimensional structure, if you have 2 electron domains, exactly the same. But if we have 3 domains, we have 3 electron domains associated with our molecule, and we're evaluating molecular geometry. 3 domains that are bonding with 0 non-bonding domains gives us trigonal planar geometry. Now remember, we had trigonal planar geometry for the electron geometry. So let's evaluate the situation for electron geometry and compare it to molecular geometry. We have 1, 2, 3 electron bonding domains, and each is 120 degrees apart. We have 1, 2, 3 atoms here, and each of those atoms is also 120 degrees apart. Those atoms form our molecular structure. So they're still 120 degrees apart. So there is no difference between the electron geometry and the molecular geometry if all of our electron domains are bonding. On the other hand, let's look at a case where we have 2 bonding domains and 1 non-bonding domain. So we still have 3 total electron domains. 2 of them are bonding, 1 of them is non-bonding. So here's our bonding domain. That's bonding domain 1. Here is bonding domain 2. And here is our non-bonding. I'm just going to put non-bonding domain right there. Again, 3 domains. But what do we know about this non-bonding electron domain? We know that this non-bonding electron domain is going to have a huge, big electron cloud that's associated with it, and it's going to put pressure on each one of these bonds. And when it puts pressure on each one of those bonds, it's going to move those 2 atoms that are bonded there closer together. So the question is, will we honestly have a 120 degree bond angle here still? And the answer to that is it'll be a slightly less than 120 degrees, but I'm not asking you to memorize what it is for every single molecule on the planet that has this kind of bonding interaction and different size atomic radiuses, because a different size atomic radius is going to impact what that final bond angle is actually going to be. And we've learned about atomic radius. All I want you to know is that we're talking about 120 degree bond angles because we have 3 electron domains. So 3 electron domains, you memorize approximately 120 degree bond angle. And then you should be able to explain to me, if you have that lone pair, it has more electronic charge, therefore more energy, therefore more repulsive force, and it's going to press on the other bonds and compress them a little bit closer together. What about 4 electron domains? So if we have 4 electron domains and they are all bonding, again, we're going to see the same thing here that we saw with the last 2, in that we're going to have 109, and again, you don't have to memorize 109.5, 109 approximate bond angles and tetrahedral structure. If we have a total of 4 electron domains, 3 are bonding, 1 is non-bonding. Again, we have a situation where, and they're showing it to you here with this big, huge electron cloud that you see that I just outlined in red. That big, huge electron cloud that I just outlined in red is going to be pushing on all of these bonds, repelling the electrons in those bonds. And that is going to compress these atoms closer together. And so the bonds, the actual bond angle here is of course going to be a little bit less than 109. But I'm not, again, going to ask you to memorize for every single atom we have that is trigonal pyramidal what that bond angle is. I just want you to realize it starts out at 109 and it can be compressed a bit. So 4 total bonding domains, 3 bonding, 1 non-bonding. That gives you trigonal pyramidal. Notice that this structure, and I'm going to erase a lot of this so that we can look at this structure again. Notice that the bottom of this structure looks like a pyramid. That's why it's called trigonal pyramidal, because that structure looks like a pyramid. And there are 3 atoms there, so trigonal pyramidal. If we have 4 total domains, 2 of them are bonding, 2 of them are non-bonding. This has a bent geometry. If you look at what they mean by bent, I'm going to outline it in red. That means we have the bent structure between our atoms because we're looking at the molecular geometry, right? So these are lone pair electron clouds that are out here. We're looking at the molecular geometry. They also call this V-shaped. I know students hate it when we have multiple different terms for the same thing, but the fact is you need to know them. Bent, V-shaped, or angular. Any one of those 3 terms can be used for this particular 3-dimensional geometry. Okay, so VSEPR molecular geometry. Molecules with 2 VSEPR groups, linear. Molecules with 3 VSEPR groups. The molecular geometry is trigonal planar. If you have 3 bonding electron groups, angular if you have 2 bonding and 1 non-bonding electron groups. What about 4 electron groups or VSEPR groups or electron domains, whichever one of those terms you like? All bonding, all 4 of them are bonding, it's tetrahedral. 3 bonding, 1 non-bonding, it's trigonal pyramidal. 2 bonding, 2 non-bonding, it's angular. Now you probably already noticed that we have 2 angulars here. Angular for 4 total VSEPR groups and angular for 3 total VSEPR groups. What I want you to notice in either case, angular is easy to pick because it doesn't matter if you have 3 VSEPR groups or 4 VSEPR groups. If you have 2 bonding, it's angular in both of those cases. So as soon as you determine you have 3 or 4 VSEPR groups and then you determine 2 of them are bonding, it's angular, regardless of whether there's a total of 3 or 4. So let's look at molecular geometry and go through a few practices here. The first thing has already been done for us. The Lewis structures are drawn. In fact, we have actually VSEPR structures drawn here for you to look at. Because they're 3-dimensional, because you see the wedges that bring the atom forward and you see the dotted lines that take the atom back through the plane of the PowerPoint screen. So number 1 has been done, Lewis structures. Number 2, now we're going to determine how many VSEPR groups we have. And that will tell us what the bond angle is. Then we determine how many are bonding and how many are non-bonding, and that will tell us what the molecular 3-dimensional shape is. So here we have 1, 2 VSEPR groups. That is 180 degrees. How do I know that? Because I memorized it. 2 VSEPR groups, 180 bond angles, degree bond angles. 2 VSEPR groups, both bonding. The molecular geometry is linear. Again, it's the same as the electron geometry would be. 2 electron domains and 2 atoms there that are surrounding the central atom. That's why. If we look at CO2, surrounding that central carbon atom, 2 electron domains or 2 VSEPR groups, 180 degrees. If there's 2 groups, it's 180 degrees. 180 degrees, doesn't matter if it's electron or molecular geometry we're looking at, it's linear. Let's look at ammonia down here on the bottom left. We have 1, 2, 3, 4 electron groups. 4 electron groups for electron geometry would be tetrahedral, but We're going to evaluate the bonding and non-bonding. We have 3 bonding, and we have 1 non-bonding. We have memorized that if we have 3 bonding and 1 non-bonding, this is trigonal pyramidal. Molecular geometry. Let's look at CH4, that is methane. 1, 2, 3, 4 electron groups. 4 electron groups, 109-degree bond angles. And I'm sorry, I missed that over here with ammonia. 4 electron groups, 109-degree bond angles. Approximately, of course. So you know this has a big electron cloud up here. 109-degree bond angles, and they are all bonding. All 4 are bonding. With all 4 bonding, it's going to be the same geometry as our electron geometry would be, and that is tetrahedral. Let's go up here to SO2. SO2 double bonds count as 1 electron group. The lone pair is the 2nd electron group, and that single bond over there is the 3rd electron group, all surrounding the central atom, which is sulfur flanked by 2 oxygens. 3 electron groups, the bond angle is 120 degrees. Okay, of course, again, big electron cloud, pushing down on those electrons, therefore pushing those oxygens closer together. So we know it's going to be a little less than 120. But our starting place, the number I want you to memorize is 120 degrees. 2 are bonding out of those 3 electron domains, and 1 is non-bonding. If 2 are bonding, remember it doesn't matter if we have 3 or 4. 2 bonding, that means it's angular, or we could call it bent, or we could call it V-shaped. Let's go over here to C2O. This is formaldehyde. 1, 2, 3 electron groups. 3 electron groups, 120 degree bond angles. Again, I memorized that. They are all 3 bonding. All bonding electron domains. That means that we have the same as we would have for the electron geometry. This is trigonal planar. Bottom one down here is water. 1, 2, 3, and 4. Sorry, went ahead a little bit there. 1, 2, 3, and 4. That means that we have 109 degree bond angles. Now we have 2 big lone pairs, and so that's even pushing a little bit more. Water somewhere around maybe 105 or 106 degree bond angle, but again, you don't have to memorize that bond angle for every different molecule. I just want you to remember the starting point, and that's 109 degrees, and then be able to explain that it's compressed somehow because of those lone pairs. 4 electron domains gives us 109 degrees. Again, we memorize that. 2 are bonding. We don't even have to finish 2 are non-bonding, because we know if we have 3 or 4 and 2 are bonding, that means that we have angular geometry. And here is a solution slide in case you get stuck when you're going through this later. And then let's look at the molecular geometry if we have molecules that have more than 1 central atom. So over here, if we look at acetylene, that is H2C2 on the top left, we notice that each carbon has 2 electron groups surrounding it. And so we have an electron group here and an electron group here. And if we went from the other side, an electron group here and an electron group in the middle. Remember, triple bond counts as 1 electron domain or 1 electron group. So that means if we have 2, this bond angle is 180 degrees. If that bond angle is 180 degrees, then both of those are going to be linear. So this molecule is linear. If we look at the middle one, hydrogen peroxide. Now, hydrogen peroxide is a little bit different because you have 2 oxygens together. You will rarely see oxygens together, but you see oxygens together in what we call peroxides, where you see O2 in a molecule someplace. The reason you rarely see oxygens together is because they hate sharing with each other. They're both very greedy in terms of electronegativity. They're very high electronegativity. They're greedy for electrons, and they don't want to share with anybody, let alone each other. So they don't pair up very often. And when they do pair up like this, and you should calculate this later, the formal charge is -1, not -2. And you should definitely calculate that later because you will be drawing Lewis structures on the next upcoming exam, because that is step 1 in solving for VSEPR. And to draw proper Lewis structures, you need to calculate the formal charge on every atom. And you'll see in this case that oxygen deviates from the oxidation state of -2 that we've said it most often has. If we look at each oxygen, because those are our 2 central atoms, this oxygen has, the oxygen on the left has 4 electron groups surrounding it. It has 2 lone pairs and 2 single bonds. And the oxygen on the right has the same thing, 2 lone pairs and 2 single bonds, so 4 electron groups surrounding it. 4 electron groups means you have approximately 109-degree bond angles. So that means that this bond angle right here is 109 degrees. 2 bonding, 2 non-bonding means bent or angular. And so you notice how this whole part of the molecule over here, and I'm just going to erase and back up a little bit, this whole part of the molecule over here, well, I was going to try to erase and back up a little bit, is bent, and I'll use red. And if we looked at the other side of the molecule, this whole side is also bent. Let's go to the last one, hydrogen azide. And we look at both nitrogens that are central. We notice the nitrogen on the left has a lone pair, a double bond, and a single bond that gives it 3 electron groups. 3 electron groups, 2 bonding. That means angular. And so you notice that this whole side of the structure over here is bent or angular, just like the hydrogen peroxide that we just looked at. And if we look at the central nitrogen that's to the right, the one with the green arrow pointing at it, has a double bond on each side of it. So it has 2 electron groups, meaning that this is going to be 180-degree bond angle, and that is linear. Now that brings us to start talking about polarity of bonds and molecules, and we talked a tiny bit about polarity and dipoles and how we use the delta symbols to label the most electronegative and the least electronegative with a delta minus and a delta plus respectively, or we can use the arrow to show the dipole. So just to recap, electronegativity, remember, has this periodic trend that increases from left to right across the periodic table, and bottom to top. Fluorine has the highest electronegativity of any element on the periodic table with a quantitative value of 4. I didn't ask you to memorize all of the electronegativity values on the periodic table, and I won't ask you to memorize them, but there are a few numbers I will ask you to memorize in terms of bond polarity. So the highest electronegativity is at the northeast of the periodic table. That's up where fluorine is. Again, increases from left to right and bottom to top. So I'm going to want you to be able to see that trend and understand that trend in making evaluations. Nonmetals have higher electronegativities compared to metals. They're not only at the northeast side of the periodic table, but remember, metals tend to lose electrons so that they can get configuration of the noble gas that's closest to them. Sodium, for example, gives up 1 electron. Lithium gives up 1 electron. Magnesium and beryllium would give up 2 electrons to get the electron configurations of the noble gases closest. Nonmetals gain electrons. They have a high electronegativity because they want that negative charge. They want that electron very badly because in gaining those electrons, they get the electron configuration of the noble gas closest to them. And this is just a diagram that's showing you that at the northeast corner of the periodic table, that's where we have the highest electronegativity. Remember, fluorine is right here, and it's got an electronegativity of 4. So let's place the following in order of increasing electronegativity. And if I had a question like this on the test, which I probably will, upcoming exam too, you're going to have access to a periodic table so that you can make this kind of evaluation. If we're looking at these 4, I'm trying to make a determination, and we want to put them in order of increasing electronegativity, so that is lowest to highest. We can quickly pick out the lowest one because we know that krypton is a noble gas, and the noble gases do not want electrons. They do not want negative charge because they are perfectly stable. So that's going to be the lowest. And then we look at the periodic table and we say, okay, where is chlorine? It's over here, very much northeast. And then where is selenium? Selenium is below chlorine and also to the left. So electronegativity increases from left to right. That means selenium in that aspect has a lower electronegativity than chlorine using the trend, and increases from bottom to top. So again, selenium has a lower electronegativity in both directions relative to chlorine. Now we want to look for vanadium, and vanadium is pretty far over here to the left, and it's a metal. So we know that vanadium is not going to be as electronegative as either selenium or chlorine because it's a metal. It wants to give electrons up. The nonmetals want to gain electrons, so the nonmetals have the higher electronegativity over on the right side of the periodic table. That means vanadium is going to be here, and then selenium, and then of course chlorine with the highest electronegativity. And so we're looking at answer A. In terms of bond polarity, we have different types of covalent bonds. We can classify covalent bonds not only now as covalent or coordinate covalent, but we can classify them as being nonpolar or polar. In the nonpolar covalent bond, we have fairly equal electronegativity. That is, equal sharing of the electrons because both of the atoms have a similar attraction for the electrons. In other words, the atoms have a very similar electronegativity in a nonpolar covalent bond. We could look at something like CH4. And again, knowing VSEPR now, we can go beyond just looking at this structure from the aspect of a Lewis structure. We know that the bond angles that are associated with this structure, because it has 4 electron domains, because they're all bonding, we know not only do we have 109-degree bond angles, but we also have a tetrahedron structure. That means all of these bond angles are 109 degrees because we know the structure doesn't look like we have it in 2 dimensions drawn right here. The structure actually has 109-degree angles, and so that means that the carbon is here. We have a hydrogen here and here that are in the plane with that carbon, but then we have a hydrogen that goes back and a hydrogen that comes forward with a wedge. And so all 109-degree bond angles, all projecting from the carbon at the same angle. That means that we have 4 outer ends to this structure. So when we talk about 4 outer ends, the carbon is in the middle. Here's one end sticking out. Here's 2 sticking out. Here's 3 sticking out. And here's 4 sticking out. That means that every one of the ends on this molecule, on this particular molecule, are equivalent. However, each one of these bonds between the hydrogen and the carbon are not equivalent. Sorry, that one's kind of messy. They're not equivalent. We have a carbon on one end, and we have a hydrogen on the other end. So if we just focus on each one of those bonds now independently, the hydrogen on one end, the carbon on the other end. Carbon has an electronegativity value of 2.5. And again, I'm not going to ask you to memorize. I'll give you these numbers. Hydrogen has an electronegativity value of 2.1. And so I can use those values to calculate the dipole here. And that dipole is 0.4. That's the difference between those two values. It turns out that 0.4 is right at the limit of being nonpolar. And I'm just going to write NP for nonpolar. 0.4. So if you calculate a quantitative difference of 0.4 between the electronegativity of 2 atoms, that is at the limit of being nonpolar. So that means that each one of these bonds that we see here are nonpolar. Each hydrocarbon bond, and so that's what we call those. We call those hydrocarbon bonds because they have a hydrogen and a carbon. So hydrocarbon bonds are nonpolar. Where do we see hydrocarbon bonds? In oils, in gasoline, in waxes, all kinds of stuff that doesn't mix with water. It's insoluble in water, like mineral oil. All hydrocarbon bonds insoluble in water. If we have, on the other hand, a polar covalent bond, so let's think about a polar covalent bond. And that polar covalent bond might be for a structure, for example, like HCl, hydrogen chloride. So if we have this kind of bond, then we calculate what the difference is between the electronegativity of each of these. Well, for chlorine, the electronegativity is 3.2. And again, hydrogen we had above, it was 2.1. And if we calculate the difference between these two, we get 1.1. And so the situation is with this particular bond and the difference being 1.1, we know that somehow that value is polar. We know that 0.4 is at the limit of nonpolar. And so the limit on either end of polar and nonpolar, so we have to be greater than 0.4 in order to be polar. But it's going to be equal to or less than 1.5. And those two are the limits of having a polar covalent bond. So again, nonpolar is 0.4 or less. 0.4 or less. And there's another slide that I have all of this written on, because this is getting kind of messy. But we notice that we have 1.1 here for the HCl, which is between these two. So we know that this is a polar covalent bond. Having the 0.4 up here, we know that the CH bond is a nonpolar covalent bond. We use these delta plus and delta minus to show that we have this fractional charge associated with these species. We don't use a delta plus and delta minus on a hydrocarbon because that bond, that CH bond, is nonpolar. But we do use those on the HCl. So we would say that the hydrogen is delta plus and the chlorine is delta minus because it's more electronegative. And if we wanted to show the dipole, then we draw the arrow like this with the plus end on the hydrogen and the arrowhead on the more electronegative chlorine. So let's ask ourselves about these bonds. Are they polar or non-polar? And one way is to draw the Lewis structure so that you can actually have a look. It's pretty quick and easy to draw the Lewis structure of H2. Water you should be able to draw the Lewis structure of now, and CH4. I'm going to help you with methanol, and then you can go back and fill in the blanks for these others after you maybe draw their Lewis structures. So if we look at methanol, we have octet electrons and valence electrons. And again, I want you to calculate these octets and these valences and calculate the number of bonds that you need, rather than just trial and error guessing all over the place. I cannot tell you on the exam how many of you did not correctly draw Lewis structures. One of the reasons is because you didn't calculate the number of bonds using the difference between the octet and the valence. The second reason is because you didn't calculate the formal charge. So those were the two main goals in drawing proper Lewis structures. Is understanding the octet is what they theoretically want and must have, but they only have the valence electrons to work with that they need to share. So that's why we are taking what we want and must have and taking the difference between that and what we actually have to determine what we can work with for sharing. Octet of carbon is, of course, 8. The octet of oxygen is also 8. We have 4 hydrogens. And so the octet for hydrogen is 2, and we have 4 altogether. So that is 3 times 8 gives us 24. The valence for carbon is 4, the valence for oxygen is 6, and the valence for hydrogen is 1, and we have 4 hydrogens, and so that is a total of 14. So we take the difference between 24 and 14, gives us 10 electrons for bonding. There are 2 electrons in each bond, so we divide that, we get a total of 5 bonds. And then if we had 14 total valence and we use 10 of them for bonding, that leaves 4 electrons to distribute around this structure. So we have CH3. And remember, carbon has to have 4 bonds. So that's why I know that carbon is going to be bonded to the oxygen, and I know that hydrogens are always terminal because they have only 1 electron to contribute to a bonding interaction. And now when we give those other 4 electrons in the Lewis structure, again, this isn't a VSEPR structure I'm drawing, this is a Lewis structure. I can make determinations if there's a bend in one of those 2 central atoms, the carbon or the oxygen, when I look at the VSEPR structure. So that will be my next thing, because when I look at whether a molecule is polar or nonpolar, I have to draw the VSEPR structure. And I'll show you quickly why. If we had the Lewis structure for water, it looks like this. That is linear. That means we have 180-degree bond angles. But the fact is, if we use VSEPR, the oxygen has 4 electron groups surrounding it. 2 are bonding and 2 are non-bonding. So the VSEPR structure is going to show this as being angular. Here, we would say nonpolar. But we don't use Lewis structure, the Lewis model forever. We expanded upon the Lewis model into the VSEPR model. And the VSEPR model is what shows us this is angular. And if it's angular, the molecule is polar. We'll talk about why that's the case in just a minute. So let's draw the VSEPR model of methanol, CH3OH down here. And if we draw the VSEPR structure of methanol, well, we can say the carbon has 4 VSEPR groups surrounding it. So there's 1, 2, 3, 4. 109-degree bond angles, and they are all bonding. So that's tetrahedral. So each of those, the 3 hydrogens are all projecting at the same bond angle, and then the oxygen is projecting at the same bond angle, but it's a different atom, a more electronegative atom. And then the oxygen itself has 4. So we could say 1, 2, we could use that same 3, and then 4. But 2 of them are bonding, 2 of them are non-bonding. So again, we have 109-degree bond angles, but it's angular. And so if it's angular, we have to change up our structure a little bit. The way that it looks from the Lewis structure to the VSEPR structure, we're going to change. The carbon is going to have 1 hydrogen that's in the same plane as the carbon, 2 hydrogens that are in the same plane as the carbon, and then the oxygen here, let's put the oxygen in the same plane as the carbon, and we can put this hydrogen going back. This hydrogen is coming forward. So that's our tetrahedral for our carbon. And now our oxygen is going to be angular. That means that the oxygen is going to have a hydrogen that is down angular this way, and then 2 lone pairs up here. That's our VSEPR structure. That's our VSEPR sketch. Oops. Pair repulsion, sorry. Let me rewrite that real quick. Sloppy. Okay, valence shell electron pair repulsion. So that's our VSEPR structure right there. Again, this is our Lewis structure. When we draw the VSEPR structure, we now know that this part of the molecule over here that originally looked like this whole part of the molecule was linear. We know when we draw our VSEPR structure that that's not the case. That whole part of the molecule is not linear at all. In fact, the oxygen is bent and angular, and the 2 hydrogens go off at 109-degree bond angles that are bonded to the carbon and the oxygen over there. So we know this angle right here is 109 degrees, approximately, a little bit less, because again, we have these big electron clouds up here. And all of these bond angles here are 109 degrees. I keep giving away the answers by bumping this computer. So that means that we have multiple ends to this molecule. So if we look at the carbon, we have at one end a hydrogen, and I'm just going to put little check marks in green by these different ends. So if we look at the carbon, we have a hydrogen, a hydrogen, a hydrogen, and an oxygen. When we look for bond polarity, we look at the atoms on either end of the bond. When we look for molecular polarity, we look at every atom that is terminal in the molecule. So if we talk about bond polarity, we know that this CH bond and this CH bond and this CH bond are hydrocarbon bonds. Hydrocarbon bonds are nonpolar. When we look at the carbon-oxygen bond or the oxygen-hydrogen bond, we know, especially this one, oxygen is way on the northeast side of the periodic table. Hydrogen is over there on the left side of the periodic table, so the northwest side of the periodic table. So we know that they are so far apart that this bond has to be polar. That means that we have 4 nonpolar bonds here and a polar bond, and then also this carbon-oxygen bond. We know that oxygen is further to the right on the periodic table in the same row or period, but further to the right. So oxygen is more electronegative than is carbon. And so those 2 bonds that I have just colored blue here are both polar bonds. Let's look at water then. Again, water has that OH bond. The oxygen is way in the northeast side and the hydrogen is way in the northwest side. And so the electronegativity difference, we don't even have to calculate the numbers. We know that it's going to be huge between these 2 atoms. And so both of those bonds are polar. I'll leave hydrogen gas, H2, and methane for you to draw out and evaluate on your own. We know the H2. We know the water's polar. We went through that one. The methane is telling you it's nonpolar, but you haven't drawn it, so you don't see that yet. And we know that the methanol is polar. So let's draw the Greek symbols. Let's go back a step and make this a little bit easy for a minute. Draw the delta symbols for the fractional charge. If we draw the delta symbols, hydrogen is delta plus, chlorine is more electronegative. It's further to the right on the periodic table, so it's delta minus. Calcium over there on the left side of the periodic table, delta plus. Fluorine on the right side, more electronegative, delta minus. Lithium on the left side, delta plus. Bromine on the right side, delta minus. And then if we draw the dipole, the arrow is going to be pointing at the most electronegative element. And how did we quickly figure this out? We just followed the trend on the periodic table. Electronegativity increases from left to right and bottom to top in the trend. So we've been looking a lot at bond polarity, and I showed you a little bit about molecular polarity. Again, the molecular polarity is the degree of unequal attraction of bonding electrons within the whole molecule. So when we look at bond polarity, let me just back up. We're looking at the atoms on either side of the bond. In every case, looking at bond polarity, we evaluated the atoms that were on either end of the bond. When we look at molecular polarity, we're going to look at the atoms that are on every end of the molecule. Nonpolar molecules have symmetrical charge distributions. Polar molecules have unsymmetrical charge distributions. So let's just look at CO2. We quickly draw the Lewis structure. And again, you're going to get really good at drawing Lewis structures because you're going to practice, because you need that tool in order to analyze anything here. So if we draw CO2, and now we analyze it by VSEPR, because you can't tell whether a molecule, you can look at a bond and you don't have to use VSEPR, but you can't look at a molecule and not use VSEPR, and I just showed you why with water. and also methanol. So when we look at this Lewis structure and evaluate the VSEPR, the three-dimensional structure, we see that the carbon, the central atom, has 2 electron domains or electron groups surrounding it. 2 electron domains or electron groups means 180-degree bond angles, and if you have 180-degree bond angles, you're linear. So it turns out that the Lewis structure and the VSEPR structure are one and the same for this particular molecule, CO2. That means that the oxygen, again, has the delta minus, and the carbons got the delta plus. So the dipole looks like this and like this. Equal and opposite vectors that cancel each other out. And so this molecule is nonpolar. Let's look at HCN, because we looked at water a minute ago. We saw that the VSEPR structure for water is bent or angular. In fact, let's look at water again a little bit more closely, because we really didn't look at it too closely now that I'm thinking about it on the last slide. So if we draw the Lewis structure for water, what we get is this. And this structure has 1, 2, 3, 4 electron groups surrounding it. With 4 electron groups surrounding it, the bond angles are 109 degrees. If the bond angles are 109 degrees, that's not 180. This structure cannot possibly be linear. So to draw those 109-degree bond angles and draw the VSEPR structure from the Lewis structure, we have oxygen here, and we have hydrogens like this, and our lone pairs are here. That gives us the 109-degree bond angle that we were looking for between these 2 hydrogens. Okay, and big electron clouds surrounding those 2 lone pairs that are pressing downward those electrons and therefore compressing those 2 hydrogens together a little bit, so a little less than 109. But the question is, now that we have this structure, and I'm going to draw the structure one more time so that we have something clean to work with. The question for this structure is it polar or nonpolar? Well, if we look at the Lewis structure over here, and this is why we couldn't really stop at Lewis structures, and VSEPR expanded upon the Lewis model, because if we look at this, we have dipoles that look like this, equal and opposite vectors, and cancel one another out. And so this molecule, as it's drawn as a Lewis dot structure, is nonpolar. Let's look at the VSEPR structure over here. If we look at the VSEPR structure, and looking at the Lewis structure again, there were 2 ends to this molecule because it's linear. There was an end over here, 1 end, and the second end over here, again because it's linear. We look at all the ends of the molecule over here after we have the VSEPR structure. Here's 1 end with a hydrogen on it. Here's a second end with a hydrogen on it. And here is a third end to this molecule. These are all sticking out as ends with an oxygen on it. So this thing is shaped angular, like a triangle. So there's 3 ends to it. It's not linear with 2 ends to it anymore. Here's the question: is one end more electronegative compared to another? And if the answer to that is yes, then this is a polar molecule. And we know the answer to that is yes, because the oxygen end is more electronegative compared to either hydrogen, either end of the molecule that has a hydrogen on it. That means that this molecule is polar. Now we can also look at the bonds and say, are they polar or nonpolar? And when we look at this bond, that's an OH bond. We looked at them on the previous slide. It's a polar bond. And this OH bond, likewise, is going to be a polar bond. So we have two polar bonds and a polar molecule here. Let's look at HCN. And I'm going to erase down here so that I have space. So here's the Lewis structure of HCN. And again, I can draw them very fast, but that's because I paid my dues with the octets and the valence, and so I know that there are 4 bonds and 1 lone pair associated with the structure. You all need to keep calculating the octets and the valence, taking the difference, finding out how many bonds. The only reason that would not work is because you have either a deficient or an expanded octet. That's the only time the math breaks down, and it tells you that you either have deficient or expanded octet. So when we look at hydrogen cyanide, we see the central atom here, carbon, has 2 electron domains surrounding it. The triple bond is 1 electron domain. The single bond is 1 electron domain. 2 electron domains, they're both bonding. That means we have 180-degree bond angles, and this structure is linear. So it turns out that the Lewis structure and the VSEPR structure are equal. Okay. So now our job is to look at the ends. Since it's linear, there's 2 ends. There's one end here, there's the second end here. And the question we ask is, one end of the molecule more or less electronegative compared to the other? And the answer to that is yes. The nitrogen is more electronegative than the hydrogen. That means that the molecule is polar. And I'm just going to say polar molecule because now we're going to look at the bonds. This is a hydrocarbon bond. 2.5 minus 2.1 gives us 0.4. That is at the limit of being nonpolar. This bond is a carbon-nitrogen bond. On the periodic table, nitrogen is further to the right than carbon. It turns out that they're side by side. So their electronegativity is really, really close. So with this bond, we need the numbers in order to determine, are they greater than 0.4 in the difference? So we're not really sure. So we can't really say until we get the numbers for the carbon and the nitrogen, and I'll leave that for you to look up later. If we have a value that is greater than 0.4, then that's a polar bond. If it's 0.4 or less, then that's a nonpolar bond. But we do know the molecule is polar. So here are the same examples we just went through by hand on the previous slide, and this gives you an idea about how to put the dipoles on these molecules a little bit cleaner than the hand-drawn models that I had on the previous page. And now we're going to look, are these molecules polar or non-polar? And so there are 4 examples here. And I'm going to do one of these for you, and then I want you to grapple a little bit with the others on your own. If we draw the Lewis structure for ammonia, Now with this Lewis structure, honestly, we don't even need to draw the VSEPR structure to make this determination. The reason we don't even need to draw the VSEPR structure is because we know we have 4 ends to this molecule. And that lone pair, which is on one of the ends, so there's a hydrogen at one end, there's another hydrogen, and another hydrogen. That's end 2, this is end 3, and this lone pair is end number 4. So that lone pair clearly doesn't have the same electron density. Even though we can't get an electronegativity of a lone pair, we can get an electron density of a lone pair. And clearly, because that lone pair is not tethered between 2 positively charged nuclei, it has much more electron density and much more electron energy. And therefore, one end of our molecule is different relative to the other ends. Even if you wanted to just look at the atoms as being ends, the nitrogen itself is much more electronegative compared to any of the 3 hydrogens, all telling us that this molecule is polar. And I'll leave the others for you to draw out so that you can have a look at them. But again, we generally have to draw a VSEPR structure to make a determination about whether or not a molecule is polar. And I highly recommend it for O2 and O3 because you're going to see some big differences between those 2 molecules when you do the VSEPR structures. So these bonding guidelines on electronegativity that I've been talking to you about are on this slide. And so these are the numbers that you need to commit to memory. 0.4 or less, greater than 0.4, but less than 1.5. And then differences in electronegativity that are greater than 2. And so that's literally 3 numerical values that you need to commit to memory to understand electronegativity. And then the actual electronegativity values of independent atoms I would give you on the test. Now let's think about this. We looked at a hydrocarbon bond, and so we could look at, for example, methane with 109-degree bond angles, tetrahedral, and we know that we have a carbon with 2.5 electronegativity and a hydrogen with 2.1. That gives us a difference of 0.4 nonpolar bonds. Let's think about something that is less than 1.5 but greater than 0.4, and I believe we looked at HCl. And Cl has an electronegativity of 3.2. And then hydrogen again is 2.1. That gives us a difference of 1.1, which is less than 1.5. And so this is polar. Greater than 0.4, but less than 1.5. That's polar. Then if we look at something that has an electronegativity difference greater than 2, let's just pick a couple of things that are very far apart on the periodic table that we've been working with a lot. For example, let's look at sodium chloride. Sodium way to the left of the periodic table, chlorine way to the right of the periodic table. We already have the electronegativity for chlorine, it's 3.2. And I can tell you that sodium is 0.9. And so that difference between those 2 is going to be 2.3. When you do the math. And so 2.3 is greater than 2. That tells us that we have an ionic bond. Greater than 2. They're so far apart on the periodic table that their difference in their electronegativity is actually ionic. That's a transfer of electrons. Okay, so there's a little trouble in paradise now, though, because we have 1.5 as a limit, and then we have greater than 2 as a limit. So what about between 1.5 and 2? There's this gray area. And we need to figure out if we're between 1.5 and 2, is this thing going to be ionic or is this thing going to be polar? And by thing, I'm sorry I said thing, I mean substance or compound. Is it going to be polar or is it going to be ionic? Let's think about a structure that may fall between those. And so methyl sodium is a structure that falls between those two. So that is a CH3. So it's like methane, but one of the hydrogens is replaced with a sodium. And so if we look at something like methyl sodium and we're asking the question, okay, is this species going to be polar or is this species going to be ionic? And probably some of you can already tell from the definitions that are there, but we're looking to see, do we have a metal and a non-metal? And we do, because sodium is a metal. So we have sodium, and then we have a non-metal, which is the carbon. So we have a metal and a non-metal. Sodium, again, has this 0.9. So let's think about what we have. And carbon has 2.5. So carbon's 2.5 minus sodium 0.9. And that, when we do that math, gives us a total of 1.6. 1.6 is between 1.5 and 2.0. And so that's in this gray area here. We evaluate, we say sodium is a metal. Carbon is a non-metal. And so therefore we have an ionic compound. It's very close to a polar covalent, but it has ionic characteristics associated with it. It's very close to a polar covalent because we're talking about 1.6, which is very close to the 1.5. So it's very close to a polar covalent, but it has ionic characteristics associated with it. All right, let's look at this learning check. And this learning check is very similar to one of the worksheets that I'm going to ask you to do when you get done with the lecture. So I have this series set up a little bit differently in that I'm asking you to do the lecture before you do the worksheets. A lot of times I'll ask you to do the work, you can start the worksheets right after the quiz, but I'm trying to get you to understand that watching the lecture is going to give you the information you need to do the worksheets. And in this case, it's going to be really important.